Welcome to Lecture 5.4, the Schrödinger Equation from Quantum Mechanics. We'll start with some history to motivate this material, though to do it justice, you really need to take a few physics courses. So Newton's second law of motion, which is mass times acceleration, is force. Here we're going to assume that acceleration is only a function of time and force is just a function of position. This actually fails on the atomic scale. According to quantum mechanics, particles have no definite position or velocity. Instead, their states, or locations, are described probabilistically by a wave function, which in one dimension is a function of x and t. We usually call it psi. And because it's a probability, if we integrate the norm squared of that over any interval a to b, we get the probability of the particle being in that interval at time t. Now here comes the black magic, and by that I just mean physics that I have not derived. So we've seen the heat equation and wave equation, and those functions are usually governed by PDEs, and this wave equation is no different. So it's governed by a PDE called Schrödinger's equation, which is as follows. So it's I h bar psi t equals negative h bar squared over 2m psi xx plus v of x times psi. So what do all these symbols mean? Well, v of x is the potential energy as a function of x, of the particle. M is mass, of course, and h bar is a constant, which is h over 2 pi, and you've probably heard of Planck's constant before. That's what h is. It's just more convenient if you renormalize this and call it h bar. Otherwise, you got lots of 2 pi's that are floating around all over the place. So Planck's constant is this tiny little thing. It's 6.625 times 10 to the negative 34, and for the units to work out, it has to be kilograms meters squared per second. Now, there's a linear operator, often written capital H for Hamiltonian, and it's this thing here. It's negative h bar squared over 2m times the second partial with respect to x plus v of x. And the reason why that is often introduced is because then this right-hand side can just be written as h psi. So Schrödinger's equation is sometimes just I h bar psi t equals h psi. A special case when the potential is zero, this is sometimes called a free particle because it's subject to no forces, is called the free Schrödinger equation. And so this term and here on the right goes away, and we have a PDE that looks like this. And this should remind you a lot of just the basic heat equation. The only difference is that now this constant has an I in here, an imaginary number, and that actually makes a difference. So think about where that might arise. I'll give you a spoiler right now. Remember how we normally get an exponential function? We get e to the negative c squared n squared t over L squared, I mean, e times some negative constant, and this thing is a damper, it goes to zero. Well, if we have an I in here, now this becomes an oscillator. Instead of going to zero, we can write this using sines and cosines, and it no longer goes to zero. So that's the big difference, is this little I. Let's turn to how to solve the Schrödinger equation. So here it is in condensed form, where h is the Hamiltonian, and here it is written out. And we'll start with the most general form, that is where the potential is not necessarily zero. So this font that I'm using, it's hard to distinguish capital versus lowercase size. These are capitals. So we will solve this by separation of variables. We'll assume that psi is a function of x and a function of t. And I made a deal about the capitalization because in most quantum physics books, you don't usually use f and g. They'll often use lowercase psi of x times phi of t. But we're not going to do that because we've been using f and t all class, and so let's just be consistent. Okay, so let's get started. So of course, psi t is f times g prime, and psi xx is f double prime g. So if we plug this back in, we get I h bar f g prime, that's this left-hand side, and then the right-hand side, we get negative h bar squared over 2m times f double prime g, that's this term right here, and then we get v times fg. So plus v times fg. So as before, we divide through by fg, and this simplifies. So the left-hand side is I h bar times g prime over g, and the right-hand side is negative h bar squared over 2m times f double prime over f plus v. So we have successfully separated variables. Everything on the left-hand side is a function of time. It's independent of position. And everything on the right-hand side is a function of position. It's independent of time. And notice this would have been much harder if potential was time dependent. We couldn't necessarily do this. So as before, if these two things are equal, they have to be equal to a constant. So we're going to, instead of using lambda, we're going to use capital E for this. That's what physicists usually use. And that's because it stands for energy. So you might have heard of quantum energy levels, like if you've taken chemistry. There are electron clouds and they have distinct levels. That's where this comes from. And of course, there's distinct or discrete energy levels if we're on a bounded domain, as we will see. If we have an infinite domain, we've seen Fourier transforms, then these discrete eigenvalues turn into a continuum of eigenvalues. And we'll see more of this later in the later part of the class. Actually, coming right up after this lecture, we'll look at PDEs over unbounded domains. Okay, so let's break this into two ODEs. So we have two ODEs. Let's write them down. Let's do the time one first. So g prime, so let's solve for g prime. So if we put everything to the right-hand side, we divide through by I. Remember, 1 over I is negative I. So g prime is negative I over h bar times, let's write IE over h bar times g. So that's our first one. And then the second one is negative h bar squared over 2m. Let's see. Actually, I don't know if I want to write. Yeah, I'll leave it like this. This is often what you'll see in physics books. F double prime over F plus V equals E. So of course I could have divided through by F, but I'm going to leave it like this. And the second one is often called the time independent Schrödinger equation. Because there's no time involved. And this first equation, this is, of course, we know how to solve this. So g of t is an exponential function, e, to the negative I e t over h bar. So I'm leaving a little space here because, of course, the general solution has a constant in front, but as we've done before, we're only looking for one solution here because we're going to multiply a solution g times a solution f and then do superposition. Okay, so if we are in a bounded domain, which I haven't necessarily said we are, but we're going to just focus on that case. So if we have a bounded domain, then let's do this. I'm going to say then there's these, take take discrete states, I'll call them Fn, and then these take discrete states, so this is n equals 0, 1, 2, etc. And then I'll put an n here and a gn here. So what's hard about this equation is v might be a really nasty function. It's hard to solve this ODE in general for realistic physical situations. Some of the simple or toy models that we'll do, this thing breaks down. Like if v is equal to 0, this is basically just what we saw with the heat equation. Again, we just have an I here instead of a real valued constant. But this holds regardless. For any potential function, this time component is the same. And notice that it's not, as I said before, it's not a damper. Normally, for the heat equation, this thing goes to 0, but now we have an I here. So that's something that using Euler's equation we could write using sines and cosines, but it's usually more convenient just to keep it as an exponential here. So also notice the special case I mentioned before is when potential is 0, then this equation is I h bar psi t equals negative h bar squared over 2m psi xx, and these two things are very familiar, things we've seen before. And that's what we'll do next. Here is an example that models that special case that I said I would do next. This is called an infinite potential well. The wave function of a free particle of mass m confined to a one-dimensional region from 0 to L, I claim is described by the following boundary value problem. So this is the free Schrödinger equation, and these are two boundary conditions. So I have to justify this and explain what this infinite potential well is. So the time-independent Schrödinger equation that we've seen is negative h bar squared over 2m times f double prime over f plus v of x equals e. So here we are claiming that v of x is 0 when x is between 0 and L. That's the domain. So here's, suppose this is a picture, this is x, say this is L, and this is of course 0. So our particle is confined in this region. So it goes back and forth somehow. It can't ever hop over and escape here. In theory, if this were like a wall or something, it could escape over if you have enough, if it has enough energy, if the potential is high enough. So if we're going to say it just really can't, then we have to say the potential is going to be infinity. So in theory, it should be just really, really large, but it's fine to approximate this as infinity. So the potential at L is infinity, and the potential at 0 is infinity. And we're going to say that it's infinity over here as well. And it's going to be 0 here. And we're just looking at this domain, so it's really just important that it's 0 on here, although by saying it's infinite elsewhere is where we get these boundary conditions. Okay, so how does that work? So let's say that outside of 0 to L, let's say that this is infinite, so the particle can't exist anywhere outside of here. So now we have two terms. We have this first term plus infinity is E, and E is some finite energy. It's a constant. It's some energy level. So this is going to be a little bit hand-wavy, but I think it's okay that if we have something infinite and something else adding up to something finite, then this f has to be 0, because this has to be like negative. Well, this can't be a finite quantity, clearly. So this thing here has to be equal to 0. I'm not saying that always infinity plus infinity is going to be finite, but I'm saying that if this is finite, that has to be 0. So f is going to be 0. So let me just write that down. So f of x equals 0 if x is less than or equal to 0, or x is at least L. And that is where these boundary conditions come from. Recall that in the heat and the wave equation, when we had these boundary conditions, that led us to F of 0 being equal to 0 and F of L being equal to 0. It's the same thing here. Okay, so now we could just jump to the end of where we left off in the last slide, just set V equals 0. But for continuity, I think it's easier if we just sort of summarize the steps here. So it'll be quick, but I think it's good. So phi of x, not phi, that's psi of x and t is f of x g of t. And so when we plug this in, we get I h bar f g prime equals negative h bar squared over 2m times f double prime g. And we divide both sides by fg as before. And this leads to I h bar g prime over g equals negative h bar squared over 2m f double prime over f. Again, this depends on time only, this depends on position only, and so this is equal to a constant that we're going to call E for energy. So we have an ODE for G. We have G prime equals negative I over H bar times E times G. And this led us to, well, let's hold off of that. I'll come right back to that. We also have F double prime equals, well, let's collect these constants together, put them on one side. And I think what we get is negative 2m e over h bar squared times f. And so now we have boundary conditions, f of 0 equals 0 and f of L equals 0. So that comes from these. So here is this very familiar boundary value problem. Let me call this constant here. Let me call that something else. I'm going to call that omega squared, just so I don't have to write down all the m's, e's, and h bars. And we know the solution to that. No. We know that fn of x equals bn sine of omega n x. As I don't have to put the bn in there till later if I want to, but that's fine. So let's see what omega, and I'm going to call this, so I'm going to do what I did before. I'm going to stick n's back in here, because we know there's one for each n, en, and call this omega n squared. So in this case, what is omega? So omega n squared is what I've circled, which is 2m en over h bar squared. And so if we solve for en, let's see. So we also know that omega n is, well, how do I want to arrange this? So let's do this here. So omega squared is n pi over L, quantity squared. So let's see. So if we set this equal to n pi, or n squared pi squared over L squared, and we solve for En, the energy level, that's what we're interested in, that's the eigenvalue, we get that En equals h bar squared pi squared n squared over 2m L squared. And so this is, think of these as like the allowed energy levels. Again, if you've taken chemistry, you've learned about electron clouds, and they exist at certain quantum states or energy states. That's what these are. And this is a feature of boundary value problems from quantum mechanics. When they are bounded, you get these eigenvalues and you get these discrete energy spaces. When they're not bounded, again, Fourier series versus Fourier transforms, these discrete steps become smaller and smaller together, and you get a continuum of allowable energies. Okay, so we are just about done. Let's see what we have to do. So let's go up to G and let's put subscripts in there. So let's call this Gn prime and put En here. So this is, okay, so what is G here? So this is negative I times that. So that's negative I times h bar squared pi squared n squared over h bar. So some h bars are going to cancel. So we get that Gn of t is, I'm going to skip the constant because they're going to absorb when we multiply that by this. So Gn of t is e to the, this constant, e to the negative I h bar pi squared n squared. Oh, I think I forgot something. I forgot a 2m. Yeah, I forgot the denominator. So there's, good thing I left myself some space. So let's put the 2m L squared there. And so the bottom here we have 2m L squared, and then we need a t. Okay, so this is what G is. So again, this does not depend on the potential x. And this is no longer a damper. This I means it's gonna oscillate. So the general solution is that psi of x t, so a quantum state of a particle is a superposition of states. That's really what we're doing here, is we're doing a superposition of these individual psi n's of x and t. So for each, I'm not going to write it down, but for each n, we have a fundamental solution psi n, which is f times, where is it? F, let's box that so we can do these both in red actually. There's G and there's F. And I'm just going to leave it like this, the omega n, because that's just too complicated. So we get a superposition, this infinite sum, which is, I'll do this in red, n equals 1 to infinity of, let's say, Bn sine of omega n x, and again omega is the square root of 2m en over h bar squared. If you want to, you can. It's just easier to write it with omega times e to the negative I h. I should have used omega in. Yeah, you know, if you don't use omega, you get this horrible mess of constants. But I think you can handle it. So it's Gn times, or sorry, it's Fn times Gn. Another way to write this is e to the negative I en t over h bar. Again, that's a e sub n. So you can see the energy state right here. So this is your general solution. Now, in the heat equation and the wave equation, there's usually an initial condition which allows us to solve for the Bn's. So in quantum mechanics, we don't have an initial state because we don't have a known location at any state. But we do have a constraint that we have not included here. So remember, this function psi is a probability distribution. It tells us the distribution of where the particle is. So probabilities, if you integrate it everywhere, they have to be equal to 1. So we have this additional condition. Let's see where I want to put it. Let's put it up here so that if you integrate this over, say, the entire real line, psi of xt, so the norm squared, you integrate this, you have to get this equal to 1, and this happens for all time t. So this actually is a probability. So these bn's have to be such that this function integrates to 1 over the entire real line, well, really only over 0 to L if we're saying that the particle has to be constrained to be in 0, 1. So figuring out what the bn's are with this constraint is well beyond the scope of this course, but it's something that is, it's a difficult problem in analysis. So I'll just say that this constraint completely determines the bn's. This is our time condition in the way that our initial condition is in the heat and the wave equation. To summarize, we saw this lecture. So consider the Schrödinger equation on a bounded domain. So that's what we saw. Of course, we can write this simpler as I h bar psi equals the Hamiltonian operator times psi. So let's suppose that this is defined on a bounded domain like this, from 0 to L. For each value of n, we have a solution of the following form: some function fn of x times this exponential function, and there's an I in here, so this oscillates, and En is the specific energy level, and that's h bar squared, pi squared n squared over 2m L squared, and this holds independent of the potential function v. Now, what makes this hard is most quantum physics problems are not quite as simple as the infinite well. Well, that's one thing, and also most quantum physics problems are in 3 dimensions. And so we will see in the next lecture, or actually not in the next lecture, but later in the course, how equations like the heat equation and the wave equation generalize to higher dimensions. And the short answer is this second derivative really turns into what's called the Laplacian, which is just the sum of the second derivatives. So in this case, it's, I would say it's n. In 3 dimensions, it would be xx plus psi yy plus psi zz. So I'm not going to talk about the Schrödinger equation at all in the course, but I'll just say that this is how this generalizes, and you will see this in the heat and the wave equation. Okay, so Fn solves, of course, an ODE, and this is the time-independent Schrödinger equation. This has nothing to do with time, assuming that the potential is not time-dependent, which, if it is, all bets are off. And the solution to this original PDE is a superposition and time evolution given by something we've seen before, a function of x times a function of time. And we also have this constraint that because this is a probability distribution, that it has to integrate to, the norm squared has to integrate to 1 over the entire region, which in this case we're saying is just 0 to L. In the special case of the free Schrödinger equation, so this is where the potential is additionally 0, and this models the infinite potential well, and this equation up here, these f's just become sine waves, so we get a very familiar looking general solution. And of course the bn's, in theory, we could solve given this constraint. I should say that sometimes you might see this because of Euler's equation, e to the I n pi x over L is equal to cosine of n pi x over L plus I sine of n pi x over L. Some books will write this solution, instead of using a sign here, I guess if you relax the boundary conditions, you might see this as e to the I n pi x over L. Again, if the boundary conditions are slightly relaxed, which not what we had here. And then you can actually combine these two exponentials, and if you were to do this, you could write this as n equals 1 to infinity of bn e to the, let's see if I can do this correctly, e, here comes the hard part, factoring, n pi x over L minus En, which of course has pi's and n's and h bars buried in it, t over h bar. So a single function like this, and this exponential has both x and t. In fact, we'll see functions like this some more in the next section when we study PDEs on unbounded domains. Okay, that brings us to the end of the lecture. If you enjoyed this material, I encourage you to take a course on quantum mechanics. Don't worry if you don't think you've had enough physics, as quantum is basically applied mathematics, and I guarantee you the mathematics that you've learned in this course, namely the PDEs in this section and the linear algebra in the beginning, will give you a tremendous advantage if you take such a class. Okay, so we're going to leave it there. Stay with us.